Hello and welcome. You are looking at tangent lines. Well, not yet. I'm going to start making them first. Let's define it, and then I'll make it, and you'll understand all of that. A tangent line is a line that intersects a circle at exactly one point. Now, that intersection point is called the point of tangency. So here's what I'm going to do. I'm going to create a line here of any reasonable color. Looks like this will be purple. And I'm going to extend it far enough so that it at least crosses through any points of the circle that I need. Now, as you can see, as I'm doing this here, it's crossing through 2 points. A point on the right and a point on the left. And if I go below it, you can tell it's crossing at 0 points and 2 points and 0 points again. So the question is, where's that 1 point? Well, I am passing it each time. It looks like it's right there. This is crossing through exactly 1 point. This would be called a tangent line. Where it's intersecting is called a point of tangency. Let's go ahead and plot that point right there. Called point, I don't know, W. Yeah, pow. There we go, point W. That's one of them. Looks like I can do a second one here. Given any point outside a circle, there can always be exactly 2 unique tangent lines drawn through that point and on that circle through a point of tangency. Where's the other one? Well, it's down below here. So I find this one, and it's crossing right there. Okay? It's another point. Let's call it, I don't know, MNOP, N, pun. I don't know. Anyway, the segments created from the points, from the point to the points of tangency are congruent. I'll dive into that not only later, but after the next point that I actually do talk about here. So what we're referencing here, let me get the right colors I want. NP and WP are both congruent segments. We'll prove that later. Okay. Also, a radius of a circle always intersects with the tangent line perpendicularly. So this circle is defined by its center. This is called circle O because its center is at O. And any segment from the center to any part of the circle is called the radius. So I'm going to go ahead and I'm going to draw 2 radii. I'm going to draw one from the center to point W and one from the center to point N. Both of these intersect with those tangent lines perpendicularly. What does that mean? It means this is a right angle. It means this is a right angle right there. Okay. And just for good measure, although we're not dealing anything with it right now, a line that intersects a circle at exactly 2 points is called a secant line. So this line right here would be a secant line, as would any of these secant, 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 tangent, neither, just any sort of line right there. Okay. Okay, radius of a circle always intersects a tangent line perpendicularly. So why is that true? I'm not really going to prove it so much as I'm going to make the example that makes the most sense. Pretend like this was the wheel of a car, or pretend like it was a hamster ball, pretend like it was a bowling ball. It doesn't matter what it is, but you're looking at the inside cross section, or at least a 2D section, because we're talking about circles and not spheres. However, even if it was a sphere, or cylinders, because the car tire, however, even if it was a 3D object, the assumption, really, although it's not exactly like that, is that the bottommost point is the only one that actually touches the ground. Okay, so like this one down here, none of these actually do. This is too thick for you to see the rest, but assume it only touches at one point. So this one is obviously a tangent line, and then this is obviously a radius, the one that goes straight down to the lowest most point, because all of these are equidistant from the center. So if that's true, and like I said, pretend like it was a car tire, okay, this is a car driving on straight ground. Well, what if there's a car that's driving uphill, like that? Okay, well, its radius still, in terms of straight down to the ground, in this sense, is still perpendicular, and this line is still tangent regardless. So as you're taking a look at this, what if the car is driving like this? And now it becomes less about a car and just more about whatever else it is. Take a look at, no matter what rotation I'm referring to, that point of tangency only has one tangent line. And it's that one that is drawn perpendicularly with the radius. The example that I was making before about such a point that was up here, and I said that it clearly couldn't go through this way, not only because it's a secant line, but as you can tell, it's also just not perpendicular with the radius. The reason why the one with the radius works is because it only touches at one point. Any other one doesn't. It'll touch at multiple points, as you can see there. So just continuing to rotate this a little bit more back to the beginning, and you'll get a full example of what I meant by that. So it wasn't so much about the point that was outside of the circle, okay, that point P. That point P can be anywhere on this line right here. It could have been right here, okay. Now here's one tangent line. Where's the other tangent line? Well, it's probably almost vertical, something like that, right? Because both of these, this one and this one, let me make this dark. These two right here both intersect perpendicularly with the two radii of the circle that go to that intersecting point of tangency, like that. So now I have these 2 points like this, and I rotate it, and once again, the same thing occurs. But the reason why I did the rotation before was to emphasize the car tire example there. Anyway, those will always be perpendicular to it. So looking back at the picture we had before shows, once again, those are perpendicular. Car tire on the ground, depending on where the car is driving, even upside down. That's fine. Okay, now that we kind of have played with that right angle thing, let's start to do some examples with that. Assume that the lines that appear to be tangent are tangent. So that means this black one here, we assume it looks tangent. So let's say it is. And then this one here. O is the center of each circle. Find the value of x. Now x is a degree measure. There are a couple ways we can go about this problem, but it always originates with one thing you must know for sure. This tangent line intersects with this radius at 90 degrees. So this is a right angle. This is a right angle. Okay. Second thing you might want to do, and here's the take-home one that I'll use for you, is for one, this is a quadrilateral. Okay. Now, you might have also realized that this is a kite. We could talk about that some other time. But this is a quadrilateral, and in a quadrilateral, the interior angle sum is 360 degrees. So if I add up 117 with two 90s, and then the x, I'm going to get 180 degrees. 360 degrees. Take away the 180 degrees here, and I get 117 plus x equals 180. I know you'd probably combine like terms here. That's fine. I'm also making a second point here. If you do any of these quadrilateral types, when the two radii are coming out like that, and the points of tangency are here, you are looking at these two guys being supplementary with each other, 117 and x. It's a very specific kind of kite with two right angles, here and here, and then you get these other two, they add up to 180 as well. And x will equal 63 degrees as a result. That's the first one. Second one here is a triangle, and which one represents a point of tangency? It looks like there's only one this time, and it's this one right here. This line is tangent, okay, or this segment, rather. This one is secant, as you can see. This one is also secant. Now, this one's also a diameter, okay? And a diameter means two radii. They go straight together, but the important thing is how this radius is intersecting with this tangent line, and they intersect at 90 degrees. So what you're actually looking at here is a right triangle, okay? A 38 degree, x degree, 90 degree right triangle. So how do you solve? You could say all three add up to 180, but as we've done with right triangles before, these two are complementary. X plus 38 should equal 90 degrees. Subtract 38 from both sides, x equals 52 degrees. So that's all you got to do with those problem types. Just kind of recognize the idea about the radius and point of tangency. Now, sometimes problems look a little more complicated. I understand that. We'll dive into one right now. This time, they give you the right angle symbol, apparently. A belt fits tightly around two circular pulleys. Find the distance between the centers of the pulleys. Okay, this one requires a little more than just the radius idea. Now it's all about understanding everything else you've learned up to that point. So what we need to find is this distance right here. Okay, I'll call that x. X inches. Okay, so where do we go from here? Well, the thing is, this doesn't necessarily make 90 degrees between a radius and another radius. As you can tell, these are both two radii here. What you might know is like, oh, look, this is 14 inches, and oh, look, this is 8 inches. But it still doesn't help you with the overall picture here. What we have to start doing is kind of recognize how these right angles here can help us. And what this can help us do is, let's draw a parallel line to this one right here over here. Because what I'm going to create now is an example, and I'm going to try to make it as parallel looking as possible. I don't know if this will work. About like that. What I'm going to create now, if these two lines were parallel, is remember this theorem. If a line is perpendicular to one of two parallel lines, then it is perpendicular to the other. So what I made here was right angle. Same with this one. Right angle. I've made a rectangle. Okay. A rectangle of base length 35 inches and height length 8 inches, which also means this is also 8 inches. Now, my job is not to find the area of this rectangle. No, my job is to solve for x. And how does this help? Well, I know that this is a right angle, and these linear pairs make this also 90 degrees. Therefore, I have a right triangle, and I do know 2 of the lengths. Let me do make this a little darker here for you. Okay. Like that. Okay, which legs do I know? I know because this is a rectangle, opposite sides are congruent. So this is also 35 inches. And I know by segment addition postulate, I know that this is 8 plus 6. That gives me 14. So this is 6 inches right here. So x is the hypotenuse of these two legs, 6 and 35. Now the one mistake, if you knew to do all of that, the one mistake you might make is assuming that your hypotenuse is 35 inches because it looks more slanted or because you assume the right triangle part was right here. Make sure you know where your right angle symbol is. It's right up there in that upper left corner. So the side opposite it is the hypotenuse, which in this case is x. How do you solve? Pythagorean theorem is good for you. A squared plus b squared equals c squared. So I'm going to whip out the calculator for 35 squared. Sometimes you just don't remember. 1,225 plus 36. So that should be what? 1,261. Take the square root of both sides. There's an exact answer. I'm going to go ahead and round it for you. I didn't ask how much I wanted you to round it. It's about 35.5 inches. There we go. That's the distance between the two pulleys. That's the part that you were trying to answer, between the centers of the two pulleys. And that's what you were trying to answer there. Now, this began with the belt fitting tightly around, so I guess you're going, this is the same. You're going to have like a bike chain problem, same kind of idea. This thing's going through tangent. It hits at one point. Obviously, it wraps around after that. But if this extended forever, you'd say, okay, it only touched at one point. There was the tangent one. Plus, they gave you right angle symbols there and there for the problem. That next part was really saying, how are we going to find this length? Right triangles are always good for that. Now, I think the idea wasn't make a rectangle first. The idea was make a right triangle first. But in doing so, you're making a rectangle, so you know some properties such as congruent, and right angles, etc. Okay, I'm going to go back to the statement that I made before, kind of a theorem. We're going to go ahead and actually prove this one. I won't write the statements and reasons out. Let's take a look at it. Two segments created from a point outside of a circle to the points of tangency of that circle are congruent. What does that mean? Well, if we do these tangent lines here, about, and here, I have to give them letters too. How else can we prove something without actually doing that? It's called A and B. All right. I want to say that in the end, PA is congruent to segment PB. Okay. So how can we prove those are congruent? Well, let's do that radius thing we were doing before. Let's draw two radii here and here. Okay. Let's also make this into two triangles. Divide this right down the middle. As close as I can. Okay, two triangles. How do we prove these are congruent? Let's prove both triangles are congruent. And then let's go ahead and use CP/CTC to say, therefore, these are true. First of all, All radii in a circle are congruent. So OA and OB are congruent. Remember, those are right angles. Radii. Second of all, the radii make right angles with their tangent lines. All right angles are congruent, therefore these two are congruent here. Okay. Thirdly, OP is congruent to itself by the reflexive property. Okay, shared side in two different triangles. Now we're looking at angle side side, which is no good. Angle side side, right? No. And just writing it this way does not change it. And no, this is not angle side angle side. I can't write it. Side angle side. You don't go side angle, skip another side and angle and go to side. It has to be the next immediate point that you can call out. You can skip at least one angle, but not two things, one side and one angle. So it's none of those, but it is HL. Hypotenuse leg. Remember, these are both right triangles, and in a right triangle, as long as the two hypotenuses are congruent, both of these right here, and one set of legs is congruent, here and here, then the whole triangle is congruent. Really, the idea behind it, if you remember, is you could use Pythagorean theorem to show that these two were congruent to each other, which is where I could actually finish this proof right here. I want to go ahead and say the HL part first, and then by CPCTC, PA and PB must be congruent to each other. They are corresponding parts, both the longer legs, or some set of legs, of two congruent right triangles. Therefore, these two are congruent. They will always be congruent outside of any point, no matter which one you choose. It could look a lot closer, and you could do the exact same proof regardless. That's the thing about Z. That's the thing about proofs. They're generalized. There are no numbers needed. It's just about saying what things are always true for what reason. These are 90 degrees, yeah, but these are always 90 degrees for this example. Okay, so I got a couple more examples here to do with you based on that idea. We're going to find the perimeter of triangle ABC in this first example right here. ABC. Okay, now understanding that last theorem is how you're going to connect everything here. This point outside of the circle intersects with the circle by extending segments AD, or AB really, and AC. They intersect at points D and F. What do these points of tangency allow you to say? That segment AD is congruent to segment AF. Okay. Same thing here. CF and CE are congruent as well. Remember, these are tangent lines of some sort. Where they intersect is where you're getting congruent parts. And then BD and BE are also congruent to each other. So in understanding that stuff, all right, here's 10 centimeters, 10 and 10. This and this are 15 centimeters. And this are 8 centimeters. Okay. Add them all up, or really 2 sets of 10 plus 2 sets of 15 plus 2 sets of 8, 20 plus 30 is 50 plus 16 is 66. Okay. All right, the next one is 66 centimeters, and we're going to label all the missing sides and lengths as a result of that. Okay, well, here's what we do know then. This is 15, this is 15, this is 17, this is 17 over here. This is unknown. I don't know how much it is, and I'm going to use the letter, I'm going to use the letter A here, lowercase a. But I know that if this is A, then this is also A. So let's find out how long these are supposed to be based on setting up an equation that says when I add all these up, it's equal to 66, just like the last one here, only different lengths. Okay, so let's do it. 2 sets of 15 plus 2 sets of 17 plus 2 sets of A equals 66. 30 plus 34. Check this out. Not drawn to scale, right? 2A equals 2. And A equals 1 centimeter. So as far as labeling the rest of this, these are both 1 centimeter each. Now, again, it's, this isn't drawn to scale. We're not making any assumptions about whatever. If you get a negative length, then there's an issue, obviously. Maybe something you did wrong, or maybe some weird way that the problem was set up. But this one's straight up just like that. Now we've labeled all of them based on this known perimeter. It just coincidence it happened to be the exact same as this one there. Fiend!